Hello everyone. Today in this video we are going to talk about input-output in computer architecture and organization. In this slide we are going to read some histories and how input and output in computer architecture and organization is helping in the development of technology. In the intrinsic world of computer architecture, input-output is the unsung hero, enabling seamless communication between the central processing unit, memory, and the myriad of peripheral devices. It is the fundamental mechanism through which computers interact with the external environment, exchanging data and information crucial for their operation. Without a robust and efficient I/O system, even the most powerful CPU would be an isolated island, unable to receive commands, display results, or store data. This presentation would delve into the core concept of I/O, exploring its various components, data transfer methods, and the continuous evolution of I/O technologies that underpin modern computing. Understanding I/O is a crucial thing for appreciating the overall performance, responsiveness, and usability of any computer system, from a personal laptop to a high-performance data center.
Okay, I'm Kenneth Mensah, and I'll be continuing from where my friend left off. So, what is input and output? Basically refers to communication between a computer system and the external world, and it encompasses all data transfers that occur to and from the central processing unit, that's the CPU and the memory. So, what do you mean that represents the communication channels between the computer's CPU and the memory, that, like as it says in the slides, and external devices. So, it's fundamental mechanism that enables one input, that's receiving data or instructions into the computer system, and output, sending processed data out from the system. So the key components, as that's indicated, there are input devices firstly, and these are devices that allow users to feed data and commands into the computer. Common examples include keyboards for textual input, as we all know, and the mouse. The next one is the output devices. Those are the ones that display the information. So the process data displays it to the users. So it converts digital data into human perceivable forms. Example, the visual format, that's the monitor, what the monitors and the projectors does. Audio, which are the speakers and the headphones, and the physical ones are the printers and those sorts. So the next one is the bidirectional devices. So as we all know, by meaning two, so bidirectional meaning it does both input and output. So as the slide says, it says many modern peripherals are capable of both input and output functions, blurring the traditional lines, which are the just input and output, basically. So hard drives, for instance, store and retrieve data, acting as both input and output mechanism. Network interface cards send and receive data packets over a network, making them essential for bidirectional communication. So, as I said earlier, they handle both input and output operations. So, example is the hard drive, as I mentioned, the Ethernet or Wi-Fi adapters, hybrid devices like the touchscreens, haptic feedback controllers, and modems. So that's it for input and output and their types. I'll finish here and let my colleague continue.
So to continue, I'm going to talk on the types of input and output devices. When it comes to the input and output devices, they can be broadly categorized based on their primary functions. So we have input devices or input peripherals. We also have the output peripherals and the input-output peripherals. So with the input peripherals, I'm going to begin with. These devices are responsible for feeding the system with data or information. And this type of data that is being inputted into the information is being collected from the environment or the user. So, for example, we have the keyboard, which is used for entering alphanumeric characters. We also have the mouse for navigating the graphical user interface and selecting items. We also have scanners for converting the physical documents or images into digital data. Microphones for capturing audio input, and we also have webcams for capturing video input. Now I'm going to talk about the output peripherals. When it comes to the output peripherals, these devices are responsible for presenting the information to the user or an external system. With these devices, they convert digital data into a human perceivable form. So that's whatever is going through the mind of the computer. Some of these things are being interpreted using these devices. So devices like the monitor interpret what goes on in the system using graphical or visual information. That's according to how we see. So it's just showing a way the system is receiving that information or data and how it's working with that data. Also, we have the printer. So the printer, which is used for producing physical copies of digital documents. So with a printer, it converts the data that we've inputted into the device and now brings it out for us to have a feel of that data. That's when you are done typing your information, you can't really touch what you typed on in the PC because it's a visual information and it uses graphics, so you can only see it. But with the help of the printer, it's able to translate these virtual or visual information into visible form or physical forms that you can touch. And also we have the speakers. The speakers, which is used for outputting audio or sound. After you speak into the mic, it also needs to be outputted what you say. And the device which is responsible for converting that sound into an output where you can hear it more or loudly, we have the speakers which help us do that. We also have the projectors for displaying images on a larger screen. So when it comes to the projector, it has a similar function as the monitors, but just that with the projector, it has the capacity or ability to project or bring out that information into a larger screen. Okay, so I'm going to talk about the input-output peripherals. When it comes to the input-output peripherals, these devices have the functionality of both input peripherals and the output peripherals. So, for example, we have the touch screens. Despite, as we know, in those times we couldn't really gain access to the screen of the PC. It's more like you just use your devices like the keyboard to interact with your PC. But now they've made it possible through input and output peripherals. It's possible now to touch your screen, to have a feel as you are touching the screen. You are seeing a change, the movement in the GUI interface. You are typing. It feels like you are really interacting with the screen, which is also very nice when it comes to input and output peripherals. We also have external drives like the USB drives, SSDs, which are used for storing and retrieving information. Every information you want to take, you put it in the drive, and also you can later come for that information. We also have network interface cards, which are used for sending and receiving data over a network. So I have modems, which convert those digital signals to analog for transmission and vice versa. Thank you very much. So my friend will continue from there and we keep flowing. Okay, so I'm going to continue with the I/O interface and bus. At the heart of efficient I/O operations lies a sophisticated architecture comprising the I/O interface and the I/O bus. These components work in tandem to ensure smooth and reliable data transfer between the high-speed internet, that's the high-speed internal component of the computer, and the diverse array of external peripheral devices. So now let's start with the I/O interface. So when it comes to the I/O interface, it's the hardware and software mechanisms that connects the I/O devices to the computer system, especially the CPU and the memory. That's allowing data transfer and control. With the I/O, some functions that it performs is it acts as a bridge between the CPU and the peripheral devices, and also it helps in managing device control, data transfer, and synchronization. Also, it helps convert data formats between the CPU and the I/O device. It also helps in handling interrupts and status signals. So some components of this I/O interface are, we have the control signals, which are responsible for managing the operation, and we have the status registers to report device conditions. We also have the data buffers, temporarily hold data during transfer. Okay, so I'm going to talk on the I/O bus. When it comes to the I/O bus, is a communication pathway that connects the CPU, memory, and I/O devices together to transfer data, addresses, and control signals. So some types of these buses are the data bus, the address bus, and the control bus. Well, from the data bus we transfers actual data, and the address bus carries the addresses of the I/O device. When it comes to the control bus, it sends control signals. It sends control signals. Also, we have the let's look at the types of I/O buses. So we have the system bus that's shared by memory and the I/O. We also have the dedicated I/O bus, which is for high speed devices. We also have the PCI, the USB, SATA. These are examples of I/O buses in modern computers. So I'm going to give general how they work together. When the CPU wants to send or receive data, it communicates with the I/O interface using the bus. Okay. Also, the interface handles communication details with the actual I/O device. The bus system ensures signals and data reach their destination properly. So that's with it. So the I/O interface basically manages communication with the I/O devices, and the I/O buses transfers data, addresses, and controls. So my friend will continue from there.
I'll be talking about data transfer methods in input or output operations, which are key to how computers move data between the CPU, memory, and input or output devices. So, in this section, there are three main methods we will cover. One is the programmed input or output. The second one is the interrupt driven input or output. And the third one is direct memory access, also known as the DMA. So let's begin with the programmed input or output, or in short, is it is PIO. So in this method, the CPU is full control of data transfer. It constantly checks the input or output device to see if it's ready. Kind of like someone who keeps looking at the stove to see if the water is boiling. So this wastes CPU time and slow things down because the CPU can't do anything else until the process is done. It's simple but not efficient, especially for larger tasks. So with the program input and or output. So it's best used for simple small tasks because it wastes a lot of CPU time. And this method is very slow and efficient because the CPU is busy the whole time and can't do anything else. So let's go to the second part, which is so the next one is the interrupt driven input or output. So in this part, this improves on the program input or output. So in short, this improves the PIO by letting the input or output device notify the CPU when it's ready. We call that an interrupt. While waiting, the CPU can perform other tasks. This increases efficiency and overall performance. However, if there are too many interrupts, especially with large data, it can still slow the system down due to overhead. Okay, so that's with the interrupt driven input or output. But like, but when the CPU gets interrupted too often, it can still slow down the system due to the frequent context switching and overhead. So finally, we edge into the direct memory access or the DME. This this is the most efficient method, especially for transferring large blocks of data. Instead of using the CPU, the data moves directly between the input or output devices and memory, hand, handled by a special component called a DMA controller. So this frees up the CPU to do other tasks and is ideal for high-speed devices like hard drives, graphic cards, and network interface. So like in summary, we say like the PIO is simple but CPU is very heavy. The interrupt-driven input or output is smarter and more efficient, and DMA is the best for fast, large data transfer, keeping the system running smoothly. Thank you.
All right. Looking at synchronization and control in input and output device, synchronization and control in input and output system are essential for coordinating data transfer between the CPU, memory, and input and output device. This function ensures that the data is transferred efficiently, accurately, and without conflict or data loss. So we have looking at synchronization. The synchronization ensure that the CPU and the output device operate at the right time with each other since they work as different speed. So here it is very fast. So we have the method of synchronization. One, we have something called pooling. The pooling here, the CPU repeatedly check the status of what an input and output device. Here it is very simple, but it wastes CPU time. Let's take example like this. For example, checking if a printer is ready before sending a file. So this is the synchronization. The first method we have pooling. For second method we have something called interrupts. The interrupt here, the input and output device send a signal to the CPU when it is ready or need attention. It is more efficient than pooling. Example, let's say keyboard interrupt when a key is pressed. So the interrupt method. So the third method, we have something called direct memory access. Here it transfers data directly between the memory and input and output device without involving the CPU continuously. Here the CPU is free for other tasks during the transfer. The idea for large data transfer, we have something like we can copying files from USB. So that's we have three methods in for synchronization. One is pooling, two we have interrupt, three we have direct memory access. So let us quickly look at the control input and output system. The control refers to managing the behavior of input and output and operations. So here the control task one, the first task is what? Device initialization. Here it's setting up the input device before use. So example, we can talking about setting a mode, a speed or a buffer size. So that's a device initialization. The second task, we have something like command. We have command insurance. So the command insurance, we have something like a send command to the device whether to read, write or what eject. So three, we have status monitoring. Here it's checking if the device is busy, ready or there's an error in the states. There's an error in its states. So four, we have error detection and handling. Here the control access is here. It identify and connecting issues like parity errors. We have disconnection or timeouts. So looking at the control aspect, with the tasks it perform, one we have device initialization, we have command insurance, we have status monitoring, we have errors detection and handles. So I want my brother to continue from here.
So I'll be continuing on slide 7, which is functions of input-output models. So one function of one of the functions are control timing. What's the meaning? What does it do? It coordinates data transfer speed between CPU and the input-output devices. That's a brief summary of it. The input-output model that manages the overall control and timing of data exchange between the processor, main memory, and the input-output devices. It issues commands to the peripheral devices. Examples: read and write. Manages the status and ensures that data transfer occurs at the correct pace. Second function of the input-output model is the buffering data. What does it simply means? It temporarily stores data to manage speed differences between fast CPUs and slower input-output devices. What I'm trying to say is that Peripheral devices often operate at significantly slower speeds than the CPU and main memory. To bridge this speed gap, input-output models incorporate internal buffers, small memory areas. Data from the faster CPU memory can be quickly written to this buffer, allowing the CPU to proceed with other tasks, while the slower peripheral gradually reads from the data. Conversely, data from a slow peripheral can be accumulated in the buffer before being bus transferred to the faster memory, thereby preventing bottlenecks and improving system throughput. The third function is error detection and status reporting. It basically identifies errors during data transfers and keeps the CPU informed of the device status. All this is trying to say is that the input-output models are equipped with mechanisms to detect and report errors that may occur during the data transmission of device operation. What does this also do? Adding parity bits to detect an odd number of bits errors. Then we have the CRC check, that's a cyclic redundancy check. More robust error detection for larger data blocks. The model also reports the status of input-output operation to the CPU, indicating whether the transfer was successful. If the device is busy or if any errors were encountered, allowing the operating system to take appropriate action.
Now let's talk about performance factors affecting input and output. So here we are going to be looking at what makes your computer fast, because CPU power alone isn't enough. Input and output performance is like the circulatory system of your machine. So if data can't move efficiently, the entire system slows down. So as you can see on the slide, the first point we would want to look at is bar speed and design. Imagine the input and output bars as a school hallway. Okay, so a wider hallway would mean that more students can walk side by side, right? And then faster walking speed. So a faster walking speed means that students move quicker, and then separate hallways means that there will be no jams. Okay, students will not run into each other. So same thing applies to what we are learning. Old systems are like narrow hallways where everyone bumps into each other, but then for modern systems like USB 3.0 or HDMI 2.1, they are like wide express hallways where data flows smoothly. For our second point, we have quality of connectors and peripherals influence efficiency. So if you've ever tried charging your phone with a cheap cable, you realize that it's slow or doesn't work at all. So similarly, a USB 3.0 drive in a USB 2.0 port runs at 1/10 speed. Okay, so even frayed cables or dusty ports cause errors like static on a phone call. Okay, so what we are learning here is that always use good cables and match ports to their max speed. So the third point says that CPU and motherboard capabilities set upper limits. Your CPU and motherboard decide the speed limit for all devices. So for example, a fast SSD is wasted if plugged into an old motherboard, okay, like a jet engine on a bicycle. And then secondly, newer CPUs support more faster lanes. Okay, so one tip you're learning here is that always check your motherboard specs before upgrading. And then when optimizing input and output, think holistically, because a fast bus, quality peripherals, and a balanced system, okay, will give you the fast computation or the fast device that you want. Because in computing, you are only as fast as your slowest link, and so considering all these factors, you can actually get the device that you want or get the output you want.
Okay, so now we are going to look at some modern IO trends and technologies. The landscape of IO technology is constantly evolving, driven by the ever-increasing demand for faster data transfer, lower latency, and greater connectivity. Modern IO trends focus on maximizing throughput and integrating intelligence closer to the data source. So now we have the high-speed interfaces. Modern systems demand fast data transfer between the CPU and IO devices. So we have the USB 3.2, USB 4, which are high-speed data up to 40 gigabits PS. That's used for storage, so video and charging. We also have the Thunderbolt 4, which combines the PCIe and DisplayPort that supports daisy chaining. And we also have non-volatile memory express. That's a fast protocol for SSDs. Uses PCIe lanes for ultra fast data access. And now let's look at the second one, which is the network IO with 100G plus Ethernet for massive data throughput. So in data centers and enterprise networks, traditional gigabyte Ethernet has given way to much faster standards to handle the tsunami of data. The amount of data being transferred is huge, or being used is very huge, and as this system was able to be placed in place, there was a change in the work performance, as in also increasing the amount of data that could be transferred, which helps in also increasing the speed of the data transfer. So for example, the 100 gigabyte Ethernet and beyond, these high speed network interfaces are crucial for cloud computing, artificial intelligence, and big data applications that require immense data movement between servers, storage, and interconnected systems. Also, we have the RDMA. So the RDMA, remote direct memory access. So technologies like the RDMA over converged Ethernet. So they allow network adapters to directly transfer data to and from memory on remote machines, bypassing the CPU and operating system, thus dramatically reducing latency and CPU overhead for network operations. And also look at the third one, we have the smart IO controllers with programmable logic and DMA. So when it comes to that, we have modern IO controllers and no longer passive intermediaries. They incorporate significant intelligence to offload tasks from the CPU. So dedicated processors and programmable logic. So many IO controllers, particularly in high-end devices like the NVMe SSDs, network adapters, and RAID controllers, now include their own embedded processors. So for example, you have the ARM cores and programmable logic. These allow them to handle complex tasks like error correction, encryption, and network protocol processing independently, reducing the burden on the main CPU. Also, we have the advanced DMA capabilities. So in modern DMA, controllers are highly sophisticated, capable of managing complex scatterguarded operations and prioritizing IO requests. This advanced DMA functionality is essential for multi-core CPUs and virtualized environments. thus ensuring that IO operations are handled with maximum efficiency and minimal CPU intervention. All the same, we've come to the end of this session, and I'm going to summarize everything in just 3 key points. The first point I want us to understand is input and output is critical for system functionality and user interaction. Secondly, techniques like interrupt and DMA help reduce CPU load and improve speed. Very important. And also, last but not the least, we have understanding the input and output architecture helps in improving the system performance. Thank you very much for joining us on this session. Do have a blessed day.